Hello everyone. This is a project I am doing for my materials class, and so I am making a genetic algorithm to solve or to try and find um, the best configuration of material within a composite. So this is a first fairly simple test. It's a four node situation that you can see over here on the right, and so it is testing different configurations using it is testing how much force that the configuration can take. Now in this situation, the top left corner is completely it has two reaction forces, an X and a Y reaction force component, and the top right corner has a Y force reaction force component, and as you can see, there is a force down in the bottom right, and so that is what is happening here. And then the program is solving for how strong the entire configuration is, um, based off of the proportional terms of the strength of the material and also the weight of the material. It's trying to optimize for a lighter frame, but also successful frames. So this is obviously a completely simplified version of this, but I am planning to scale this up to a more sophisticated level for the project. So I don't know if I'll be streaming that today, but I wanted to just have this up for uh, people to view the results, as well as for myself to have documentation of the project. So I guess enjoy, and it looks like I have a error in the code to start out, so I'm going to be looking into that. I'll probably start the stream back up in a few minutes. Okay, this is take 2 on the materials project. I'm going to restart it so that we can see what's going on. The problem was that I did not create the folder that it was looking for, so it was not able to save the data right when it got to the end of the generation. So that is what you're seeing, and you should be able to see the screen now, and we will start it back up. So this is restarting from the beginning, but this is a relatively small size for the population in total. The total population is actually just 50, as you can see from that number that just left the screen up at the top. There are 50 children in each generation. From those 50 children, the program selects the top 10 children and moves forward with those in order to try and find a optimal configuration through genetic evolution. So that is currently what's happening, and I will update you if anything happens significant. Okay, as you can see, there is a secondary problem, but I'm going to be looking into that, so I will be right back. As I mentioned, this is somewhat of a debugging process for the simpler case, so we will be attempting, let me go clean out the contents of the folder so that we're not getting the unnecessary data. I probably could have kept that as a trial 1, but we only went through one generation, so that doesn't really give us much information. So we are going to continue this. This is for node number 1, and and we will start it back up. It's an interesting configuration. It had all aluminum. That is a possibility, and so one thing I should mention is that the properties of the different materials are proportional to their actual properties. They are not they are scaled down just for simplicity in math. So as it goes from weight, I took the densities and simplified them down to say the density of steel is around 8,000. So the weight of steel in this case is 8. And that is just used to create the score or the fitness you're seeing over on the left. So that is what that. So the fitness score is the force at which it is optimal. So the force that it can withstand, which is the current force that you see fluctuating up in the top, and that white bar also on the bottom right corner. So the fitness score is the force divided by the weight, and the total weight is the collective sum of the weight of the individual linkages. So that is something to play into the whole situation. So it does look like we successfully went on to generation 2. So we should be seeing, I don't know that we'll be necessarily see some patterns coming through, but what we should see is that top score of 39,000 should go up, assuming that the process is working correctly. But that's not guaranteed, because the way that a genetic algorithm works is that it takes information from the previous generation, but there's also some mutation. And especially in a case that's this simple, it wouldn't be outlandish to see every once in a while a generation that does worse. But this is the process of this is that the pattern should trend towards a higher score. So that is what we're looking for, and I will inform you if anything significant happens. Okay, as hoped, we see that the next generation has done better. I do believe that is the same score in the next best, just because of the way that the algorithm boils down to. That's not necessarily true. That could be slightly different. But the way that the algorithm is settling down on a optimal force is it actually starts at a force that definitely breaks the system, and then cuts that in half. And what it keeps doing is every time it fails, it goes down by a bisector of the current amount, and every time it's completely successful, it goes up by that same bisector. So say we had a force of 50,000 newtons being applied, and the system was successful. Then it would cut 50,000 in half, bringing it to 25,000, but it would add that to the 50,000. So the next force it would try would be 75,000. But the step at which it changes is what's being bisected. So after the 75 is checked, say that at 75,000 newtons the system breaks, then the last step that we did was 25,000. So the next step that we're going to take is 12.5 thousand. So it would subtract 12.5 thousand down to 62.5 thousand and try that force until it bounces in towards the optimal situation. And because of the amount of times I'm doing that 30 times each round. It and Based off of the starting point of what force is used, I believe that's 10 million. That was just a value that I found trial and error would break the system, and it was a nice benchmark number. It starts at 10 million, so after doing it 30 times, it's approximately accurate to 1/100th of what the force should actually be. So that is the error on the force, but it should be accurate enough, especially in this simple case, in order to give us a fitness score that is aptly showing us what the program is capable, or what that configuration is capable of. Okay, so it looks like we are trending upwards, which is a good sign. We do see that that top score is now 53,000, and we still have that second best score of 39,000, but that is probably just because it's a configuration where there was no mutation from the past where that was the best score. So that's something that we may see um, a lot of, and that's something that tends to happen in the genetic algorithms. Is you will see you will see pretty near copies, especially in a simple system like this. You will see pretty near copies of or exact copies of the previous generations. In a more complex system with more linkages to adjust, it would be significantly harder to see those exact copies, but there would be sort of a species that would evolve out of individual uh, individual parents from previous generations that were relatively successful. As I mentioned, it is possible to have a generation that does recess a little bit, and that's what we're seeing in that past fifth generation. It went down to 49,000. So, with this simple case, it is possible that the optimal configuration has already been tried. So, this is just something that I wanted to test the waters of how this works. And the way I've set this up, the entire program is built to work no matter what the configuration is. So I can just adjust the configuration to be significantly more complex. What I'm thinking I'm going to do is have a curved beam where there is a force applied to the end of it, just to see how that plays out in the total system. And I want to have a lot more complexity. So we're not going to have this large of a image. Um, these linkages won't be this large on the screen. There'll be tiny linkages, and there'll be a significantly larger amount of them. I do see an 81,000 that just popped up. That's pretty significant. That should be the highest we've seen so far. So, and maybe I was wrong in the amount of digits, or maybe my bubble sort has a problem. So that might be something I have to look into going into the next trial. But we do see that that second best is now slightly better. So that's something that is promising. And what you can notice is that we're seeing a lot more 5-digit numbers in the scores. So that is something that is expected, but also it's nice to see in general. Okay, I did check. I have it set for 20 generations. I think that may be enough to bring it to exhaustion, just because of how simple this is. As I mentioned, it's fairly easy to find an optimal configuration for this, just because the number of permutations for this there's only 5 linkages, so the amount of different combinations of linkages, well, I guess it'd be permutations because order does matter in this one, is fairly low compared to if we upped that even to 10. So what I'm aiming for in the future, when I do add the extra complexity to it, is to have something on the order of maybe like 100 linkages, which significantly increases the permutations and rules out the possibility of just exhausting all of the options. Um, and so that's where we see the genetic algorithm really coming into the light as a nice method for solving a system like that. One thing I'm noticing, if you look at generations 41 and 42, you see that those numbers are identical, and that's not the first situation. I believe 36 and 37 at the top of the screen were also in that situation. Um, all right, so yeah, there is a problem with the scoring system. I'm not sure what's happening with the bubble sort, but for some reason you can see that that next best value not is bigger than the top score. So that's not correct, but I'll have to look into that. Um, but it does look like the way that it's testing the fitness and the actual saving of everything seems to be in order. So um, just seeing that, I don't think that it's worth it to continue this trial. But I do think that this gave me some valuable information in order to improve the system so that it will be successful when we try this on a more complex system. But as I was mentioning, just to get that out, you'll start to see a lot of children that are getting the exact same scores, and that means that we're starting to see a bottleneck in the actual um, uh, layout of the population. So that's where it's starting to dwindle down to an optimal solution, or pseudo-optimal, as genetic algorithms have the possibility of missing the optimal solution. Okay. I think what we'll do is, since there's only 50 children, I will let this 10th generation run through, and we will call it quits there. Um, but I think that this was, as I mentioned, a successful um, trial, just if anything for the debugging purposes. Um, and it is showing me that the simulation is working as an FEA um, uh, program. So that is what I wanted to see. So as this wraps up, thank you for watching, and I will be probably streaming this, maybe not another one tonight, but definitely tomorrow I will be doing a large amount um, of testing in order to gather data for the project. So that is going to be it.